Welcome to a short tour of NPUs and how they turbocharge machine learning at the edge. This talk shows an NPU sitting between general compute like CPUs, GPUs, and edge devices, acting as a specialized accelerator that lets models run locally on cameras, drones, and phones while preserving responsiveness and lowering energy compared to cloud offload. The edge creates tight constraints, limited battery, thermals, and compact form factors, and traditional GPUs often exceed those power envelopes, forcing cloud offload and hurting privacy and latency. NPUs restore on-device feasibility by delivering high TOPS per watt, keeping data local, and meeting strict millisecond SLAs so sensitive workloads can run privately and responsively. Matrix multiplication dominates neural nets, and DRAM trips create a memory bottleneck. So NPUs use systolic arrays to stream weights and inputs with massive data reuse. That architecture minimizes external memory access, speeds up gem operations substantially, and cuts power, turning memory-bound problems into compute-bound wins and enabling much faster, more efficient inference on constrained devices. Unlike shared L2 cache designs in GPUs, NPUs favor distributed SRAM banks collocated with tensor cores and DMA prefetching to hide latency. This reduces external bandwidth pressure by roughly 5 times, which is critical for high-resolution 8-bit inference, such as 4K video, where lower latency and predictable throughput matter more than raw bandwidth designed for graphics workloads. Benchmarks with MobileNet v3 illustrate the advantage. NPUs can hit single-digit millisecond inference times and sub-watt power usage compared to integrated GPUs, translating into roughly 4 times battery life for some workloads. In real-world drone use, that efficiency can add tens of flight minutes while maintaining 30 frames per second object tracking, proving specialization beats brute force when every joule counts. Scaling to real-time 4K AI requires chaining NPUs and exploiting parallelism. Layer partitioning, dynamic batch tiling, and pipeline parallelism let systems scale from a single chip to 416 NPUs. Hardware schedulers and load balancing cut tail latency significantly, enabling mixed criticality tasks like face unlock, voice commands, and AR overlays to run deterministically on the same platform. Successful deployment demands co-design across models, compilers, and hardware. Start by pruning and quantizing models early. Fuse operators and align tensor shapes. Then use automated compilers to map workloads across CPU, GPU, and NPU. The goal is to maximize buffer, reuse, and fit working sets on chip, so video frame budgets like 16 milliseconds are met reliably under real thermal and power constraints. NPU SDKs are still evolving, and vendors bring different toolchains, opaque performance counters, and limited low-precision kernels, which complicates development and debugging. Strategic mitigations include adopting open intermediate representations for portability, keeping GPU fallback paths for robustness, and budgeting extra validation cycles for silicon and driver revisions to ensure long-term software sustainability. Heterogeneous compute platforms like Intel Core Ultra and AMD XDNA illustrate the benefits of a shared memory fabric where CPU, GPU, and NPU tiles cooperate. With direct KV cache hops and reduced PCIe copies, on-device fine-tuning loops save energy, delivering multifold improvements in efficiency while enabling personalized models to remain local for privacy and compliance advantages. Architectural advances are addressing transformer growth by combining sparsity engines that skip zero weights with larger on-chip SRAM budgets, enabling orders of magnitude more local parameters. The result is a path toward hundreds of billions of parameters on edge systems within tight power envelopes, and future-proofing via PIM-DRAM and local models to minimize cloud dependency and network costs. When choosing where to run workloads, pick NPUs for battery, or thermally constrained devices under roughly a 2-watt envelope for deterministic low-latency inference, and when models quantize to INT8 and fit on chip's RAM, stay with GPUs or cloud for large batch training or double precision needs, and treat NPUs as offload partners that complement, not replace, existing compute resources. A practical deployment framework follows 4 phases. audit and profile system and model constraints, optimize and select silicon with open compiler support and early quantization, bench and validate performance under thermal soak while keeping a GPU fallback path, and finally secure supply agreements, plus continuous integration testing across microarchitecture variants to ensure long-term reliability and support.